6 meteoroid impacts hit the moon last night in under 1 hour, and 4 astronauts watched it happen with their own eyes from 252,000 miles away. NASA's ground-based monitoring program has recorded roughly 300 impacts in 20 years. The Artemis II crew saw 6 in 57 minutes. By the end of this video, you will understand why that number has scientists questioning everything they thought they knew about the space around our planet. Last night, at approximately 8:35 p.m. Eastern Time, 4 astronauts aboard NASA's Orion spacecraft watched meteoroids slam into the surface of the moon, not on a screen, not through a telescope. With their own eyes, from a spacecraft window 252,000 miles from Earth. It is the first time in the history of spaceflight that humans have witnessed lunar meteoroid impacts in real time. Commander Reed Wiseman was the first to call it out during the live webcast. "We saw at least 5, he said. The flashes appeared near and south of the moon's equator on the near-side hemisphere. Brief bursts of light as objects traveling tens of thousands of miles per hour struck the airless surface and converted their kinetic energy into craters and light. Then pilot Victor Glover spotted a 6th flash near the moon's south pole. 6 impacts in approximately 57 minutes. The crew described being giddy at the sightings, and for good reason. They were seeing something that until last night existed only as data points in a NASA database. This was not a planned observation. The crew was watching a solar eclipse, the first total solar eclipse ever witnessed by humans from behind the moon. Totality lasted 57 minutes. From Earth's surface, a total solar eclipse maxes out at about 7.5 minutes. But from Orion's position on the far side, the geometry held for nearly an hour, and with the sun completely blocked, the entire near side of the moon went dark. That is the only reason they could see the impacts at all. Meteoroid flashes are faint. They last a fraction of a second. But against a fully dark lunar surface with no atmosphere to scatter light, the crew had a view that no human being and no ground-based telescope has ever had. The Artemis II mission itself is historic on multiple levels. It launched on April 1st from Kennedy Space Center, the first crewed mission beyond low Earth orbit since Apollo 17 in December 1972, a 54-year gap. Yesterday, Orion reached a maximum distance of 252,756 miles from Earth, surpassing the record set by Apollo 13 by 4,111 miles. These are the farthest humans have ever been from home, and what they saw in that window is now raising questions that NASA's own scientists are working to answer. Here is why 6 impacts in 1 hour matters. NASA has been monitoring the moon for meteoroid impacts since 2006. The Lunar Impact Monitoring Program operates out of the Meteoroid Environment Office at Marshall Space Flight Center in Huntsville, Alabama. They use 2 purpose-built telescopes and astronomical video cameras to watch the moon's unlit crescent, the portion illuminated by Earthshine, on about 10 nights per month when the solar illumination angle is between 10 and 50%. Over 20 years, that program has confirmed approximately 300 impacts. That works out to roughly 15 to 20 confirmed detections per year. In a good month, they might confirm 1 or 2. The Artemis II crew saw 6 in 1 hour. Now, the immediate objection is observation geometry, and it is a fair one. The ground-based program can only see a narrow sliver of the lunar surface, the Earthshine crescent a fraction of the total near-side. The crew, from behind the moon during a total eclipse, could see the entire near-side night face at once. That is a dramatically larger observable area, and it absolutely accounts for some of the elevated count, probably a significant portion of it. If you can see 10 times more surface, you should detect more impacts. That is straightforward geometry, but here's the part that does not get explained away so easily. The ground-based program uses CCD cameras, electronic detectors that are far more sensitive to faint, brief flashes than the human eye. These cameras can pick up impacts that produce flashes too dim and too brief for any person to notice. The sporadic background rate those cameras detect is approximately 2 to 3 impacts per hour under optimal conditions. The Artemis crew, using only their eyes, a fundamentally less sensitive detector, recorded 6.3 impacts per hour. They were using a worse instrument and getting a higher rate. Either their observational advantage from seeing the full night side was even more significant than the geometry alone would predict, or there were simply more impacts happening during that window than the sporadic background models expect. And this is where the Artemis observations collide with something that has been building for months. In late March, the American Meteor Society published a comprehensive statistical analysis of Q1 2026 fireball data. They looked at every reported fireball event from January through March and compared it to historical baselines. The numbers were not normal. The AMS found that fireball events witnessed by 50 or more people had more than doubled compared to baseline. 38 events versus a historical average of approximately 18. That is a 4.5 sigma anomaly, the kind of deviation that, in most scientific fields, would be considered near certain evidence that something real has changed. Sonic boom confirmation rates hit 79%, meaning a far higher proportion of incoming objects were large enough and fast enough to produce audible shock waves that reached the ground. Long-duration sightings, fireballs that stayed visible for extended periods, totaled 1,693, which is 2.5 times the previous record. And perhaps most striking, 2 HED meteorite falls, a rare class of achondrite linked to asteroid 4 Vesta, occurred within 9 days of each other, separated by 98.2 degrees on the sky. Getting 2 HED falls that close together in time and that far apart in sky position is statistically improbable from any single source. The AMS conclusion was precise. The distribution did not broaden. It shifted upward. Objects entering Earth's atmosphere in Q1 were systematically bigger, slower, or more energetic than normal. The enhancement concentrated around known sporadic meteoroid sources, the enthelian source and high declination radiance, consistent with an amplification of existing populations, not a new stream from an unknown source. But one question hung over the entire analysis, and it is the question that skeptics immediately raised. Is this real, or is it reporting bias? More people have smartphones now. AI-powered reporting tools have made it easier than ever to log sightings. Social media amplifies events that might have gone completely unnoticed a decade ago. The AMS acknowledged that AI-amplified reporting may contribute to the numbers, but they concluded the statistical signal exceeds what reporting bias alone can explain. The sonic boom rates, the HED falls, the distribution shift, those are physical measurements, not social media impressions. And that is exactly why what happened last night on the moon matters so much. The moon has no atmosphere. It has no observer networks. It has no smartphones and no social media. When a meteoroid hits the moon, the only thing that determines whether it is detected is whether it happened and whether someone was watching. The moon is the ultimate control group for the question the AMS could not fully answer from Earth alone. If the near-Earth meteoroid environment genuinely shifted in early 2026, if there really is more material out there, bigger objects, concentrated in known sporadic radiance, then the moon should be getting hit more too. Not because of reporting, not because of AI, because there is physically more stuff hitting it. The physics does not care about observer networks. The Artemis II crew's 6 detections in 1 hour do not prove that by themselves. The sample size is small, 1 observation window, 1 unique geometry, 6 events. You cannot build statistical significance on 6 data points. But what you can say is this. The observation is consistent with the elevated flux hypothesis. The rate was at the upper range of what sporadic flux models predict for the crew's viewing geometry. And that is with the naked eye, which should be detecting fewer impacts than cameras, not more. If the crew had seen 0 or 1 impact, that would have been unremarkable. 6 is notable. This is potentially the first off-world data point supporting the AMS findings. If confirmed through additional analysis, and confirmation could come soon, it would fundamentally shift the conversation. It would mean the Q1 anomaly is not an artifact of how we observe from Earth. It would mean something has actually changed in the meteoroid environment around our planet and its moon. And that raises a much bigger question. Why? There's another angle that makes this even more significant. Since all 6 impacts occurred on the moon's near side, ground-based amateur astronomers who were monitoring the moon on April 6th may have independently captured some of the same flashes. If any of those detections can be cross-referenced with the crew's observation timestamps, it would produce the first ever simultaneous space-based and ground-based observation of a lunar meteoroid impact. That has never happened in the history of astronomy. It would enable direct measurement of luminous efficiency, the fraction of impact energy that becomes visible light, which is currently one of the largest uncertainties in all meteoroid flux calculations worldwide. The eclipse that made these impact observations possible was itself a scientific event unlike anything that has been recorded before. Canadian astronaut Jeremy Hansen reported that the solar corona was visible for at least 10 solar diameters from the lunar limb. During a total solar eclipse from Earth's surface, the corona is typically visible out to about 2 to 3 solar radii from the limb, before it fades into the atmospheric background. From the vacuum of space, with 0 atmospheric scattering, the crew could see the corona's faintest outer structures far beyond what any ground-based observer or instrument has ever recorded. That outer corona is one of the least understood regions of the sun's atmosphere, and these observations may reveal new details about coronal streamers in the transition zone where the corona becomes the solar wind. Mission specialist Christina Koch captured a photographic sequence of the eclipse, including images of lunar mountains and topography silhouetted against the corona along a wide arc of the moon's edge. Those images are being downlinked now, and NASA has scheduled a press conference for this afternoon, April 7th, 4 p.m. Eastern, to release the first photographs. Commander Wiseman described the Earthshine illuminating the otherwise dark lunar terrain in terms that suggest the crew understood the magnitude of what they were seeing. The Earthshine is unreal. Humans have not evolved to see what we are seeing. It is hard to describe. It is amazing. But here is the critical connection back to the impacts. Without this eclipse, there are no observations. The 57-minute totality window, nearly 8 times longer than any eclipse from Earth, is the only reason the crew could see the lunar night side clearly enough to detect faint impact flashes. The eclipse was not just a beautiful moment, it was the instrument that made the discovery possible. And while the Artemis crew begins their return journey, the near-Earth environment is about to deliver another reminder that our neighborhood is busier than most people assume. Asteroid 2026 GD will pass Earth on April 9th at 2300 UTC at a distance of 0.65 lunar distances, approximately 155,000 miles. That is well inside the Moon's orbit. The object is estimated at 10 to 20 meters in diameter, based on its H magnitude of 26.556, roughly bus-sized to house-sized, traveling at 12.65 kilometers per second, which is about 28,300 miles per hour. This is not a threat. The orbit is well characterized, and there is zero collision probability, but the timing is impossible to ignore. A sublunar asteroid flyby on the same day the crew is on final approach for splashdown, and it is not alone. 3 asteroids will pass within 5 lunar distances in a single 3-day window this week. Combined with the meteoroid impacts the crew just witnessed on the Moon and the Q1 fireball surge documented on Earth, the picture that is building is consistent. The space around our planet is more active right now than it typically is. The question that keeps coming back is whether this is normal variation that we are finally noticing, or something else. The 4 astronauts who just made these unprecedented observations are now facing the most dangerous phase of their mission. On Friday, April 10th, Orion will enter Earth's atmosphere at approximately 25,000 miles per hour, Mach 32. That will be the fastest crewed re-entry ever attempted in the history of human spaceflight. The heat shield is Avcoat, an ablative material designed to char and erode in a controlled way, absorbing the extreme temperatures of atmospheric re-entry. During Artemis I, the uncrewed test flight in late 2022, NASA found over 100 locations where the Avcoat charred in ways that were not predicted. The root cause was traced to gas trapping during the SCIP re-entry profile, where the capsule dips into the atmosphere, bounces back out into space, and then re-enters a second time. The thermal cycling of that double entry maneuver caused gases to become trapped in the Avcoat material, leading to unpredicted char loss patterns. NASA's solution? Eliminate the skip entirely. Orion will perform a direct re-entry on a steeper, faster profile, which should prevent the gas trapping mechanism from occurring. But this direct re-entry profile has never been flown with crew aboard. Former JSC Director of Engineering Charles Camarda, an STS-114 astronaut who flew on the first shuttle mission after Columbia, has publicly drawn parallels between the current Artemis heat shield situation and the institutional patterns that preceded both the Challenger and Columbia disasters. His concern is not necessarily with the physics of the engineering fix, but with the institutional pressure to declare a problem solved when significant unknowns remain. He has pointed out that in both previous shuttle disasters, engineers raised concerns that were overridden by schedule and political pressure. Those concerns from Camarda have not been publicly addressed by NASA leadership. Splashdown is targeted for approximately 8:07 p.m. Eastern on Friday, off the coast of San Diego, with recovery operations aboard the USS John P. Murtha. The crew who just witnessed the Moon getting hammered by space rocks, who traveled farther from Earth than any human in history, now has to survive the trip home through the most extreme re-entry conditions any astronaut has ever faced. There are several developments over the next 72 hours that will determine how significant last night's observations really are. First, NASA's press conference this afternoon at 4 p.m. Eastern will release the crew's Eclipse photographs and surface images. The scientific community will be analyzing those images, not just for their beauty, but for any data that can be extracted about the impact events themselves, precise timestamps, locations on the lunar surface and brightness, estimates that could help characterize the impactors. Second, the ground-based cross-reference. If amateur astronomers who were monitoring the Moon on April 6th captured any of the same impact flashes the crew reported, Those matched detections would constitute an entirely new type of scientific measurement, the first simultaneous space-based and ground-based observation of a lunar impact. The professional and citizen science astronomy communities are already comparing observation logs and timestamps. Third, the radiation environment. The electron flux around Earth has been above the alert threshold for 4 consecutive days, and the trend is climbing. 2,419 on April 4th, 5,995 on April 5th, 6,075 on April 6th. The Artemis crew is flying through that environment without the protection of Earth's magnetosphere. While proton flux remains at background levels, the sustained and escalating electron environment matters for Orion's electronics and the crew's cumulative exposure calculations. And then there is Friday, the re-entry, Mach 32. A heat shield that surprised its designers on its first and only test. A re-entry profile that has never carried humans. 4 astronauts who just traveled farther from Earth than any person in history, who watched the moon get struck by space rock 6 times in 1 hour, who saw the solar corona in ways no human eyes have ever seen it, and who now have to trust the engineering to bring them home through a wall of plasma at 25,000 miles per hour. The near-Earth environment may or may not have changed. The data from the moon is suggestive but not conclusive. The AMS analysis is statistically compelling but debated. What is not debated is this. For the first time in 54 years, humans went far enough from Earth to see the evidence for themselves. And what they saw has scientists scrambling for answers.